So yeah, thanks for joining us, Lorenz. Good to see you today. For everyone watching, maybe we could start by you introducing yourself, please.
Absolutely. Thanks for inviting me today, Charlie. So I'm Lorenz. I've worked in the data center space globally, all regions of the world, really enjoyed working with teams, learning and growing. And I've had the opportunity to work for three major businesses, Johnson Controls, Vertiv, and Train. So it's been a wonderful journey, have a lot of good friends, and look forward to sharing a little bit today about the industry.
Yeah,
Thanks for the
perfect.
time.
Yeah, you're very welcome. Yeah, very interested to pick your brains as well, Lorenz, and I think a lot of people will get a lot of value from hearing from you. So yeah, just to kind of preface, then I'll give everyone an introduction as to what we're going to be speaking about, and then we can get into it. So the topics that we have decided to cover predominantly stem around transitioning from an air-cooled environment into a liquid cooling setup within a data center. So we'll cover that. We'll also touch on the heat rejection challenges. That seems to be a big point at the moment that a lot of people have some concerns about. And then finally, we'll go into the rack density and local heat rejection into white space. Um, so yeah, to start things off then, what do you see at the moment, Lorenz? What's kind of driving this shift from traditional air cooling into liquid cooling of data centers?
So everyone's really aware of the high-powered compute, the digital compute and the like, driving servers that process more, which therefore typically run at higher heat loads and densities. So these servers, as these chips continue to rise, the goal is to remove that heat. We all know there's no such thing as cooling, there's the absence of heat. So there's no such thing as cooling, we need to remove that heat, and when doing so, the heat load on these servers as it changes, ultimately air versus any kind of liquid, water or other densities, it's much, much more efficient to cool liquid. Typically, liquids are about 1,000 times more dense than any air type solution. So there's an opportunity for us there. Even if we design them poorly, physics is on our side.
Sounds good. So what are the kind of main limitations then of things today, specifically for the air cooling? You say we need to move away from that. Why is that?
It's not that air cooling isn't working for us, it's that it's not going to work for us in the data center space as the server temperatures continue to rise and the capacities rise. Right now, if you look at the roof or the surrounding facilities of any data center, it's filled typically with HVAC units, whether they're chillers or DX with direct expansion, direct evaporative, you pick the type of solution, it surrounds the grounds and usually fills the roof. Therefore, when you go to a higher density solution, I need more capacity. You can't stack units on top of units. So we need to change the game from air to some sort of a hybrid liquid solution.
Very interesting. And you touched on it earlier, around the fact that physics is on our side, but what do you see that air cooling can bring to the table then that perhaps the liquid cooling can't?
Liquid cooling will always, both will have a play. And if we think about air cooling, right, there'll still be human occupancy. There's still going to be a lot of the IT cabling. And then finally, there's still going to be a lot of equipment that's not liquid cooled, whether it's the switch gear, the UPS, the batteries, and the like. So there's a play for air. There's always a question around what percentage of air versus liquid and how it's going to grow. But we ultimately see that air will have a play. And the goal is how do we most efficiently deliver both to these data centers, whether they're greenfield sites or retrofit at the brownfield sites.
Yeah, okay. Very interesting. And this is obviously quite a new play, as you say, with the invention of these chips. It's still fairly new to a lot of people. So what are you seeing today as some of the biggest challenges that are causing people problems currently?
Mm-hmm. So I want to step back a little bit. So we wouldn't say liquid cooling is new. What happens is it's more sexy now. It's more in front of us. There's been high density cooling for a while. Whether someone had several racks in a small closet, meaning there wasn't a lot of airspace for them, or that they chose to have higher density compute before, we'll call high density, which liquid cooling is a subset, right? High density has been around for well over a decade, if not more. Yeah, more like 15 years. So there's solutions that are in place. But going forward, we see that the significant increase, anyone can Google up what's been happening to these server chips in terms of heat loads. They're 200 watts, 400, 800 watts per chip, times multiple up to 8 chips per server, times multiple, 6 to 10 servers per rack. And remember, a rack is about 7 feet tall, 2 feet wide, and 4 feet deep. So if we just kind of think in our mind for a moment, they used to be 10 kilowatts a rack. So for those in the US, we think in tons. That's like 3 cooling tons. So one rack, 8 square feet, so 2 feet wide, 4 feet deep. It's about as much cooling as a standard residential home in the US. So now they're going to go to up, 50 to 100 kilowatts per rack. So now it's 100 times. So think of 10 times. So think of 10 homes, 10 home cooling units in the equivalent space of 2 feet by 4 feet, so 8 square feet. So significant amounts of loads. Again, if your home was, or your flat was a data center, your roof would already be filled with condensing units trying to reject that heat, and then you just have to stack more on top. So we know there's a play for the higher density solutions.
Yeah. Okay. Very interesting. So, I mean, it sounds like a lot of things could go wrong then, in that kind of environment. What are some of the things that people maybe should be aware of when they're moving into this phase?
Mm-hmm. Kind of the two that top is we think of risk factors, really leakage, right, dominates. We can't really have any kind of leakage within the space. And then services. So the ability to swap out your servers. There's multiple different tiers of data centers. There's 4 tiers. A tier 1 is like standard data, Facebook, data mining. You have no redundancy and you tolerate your data goes down. It's typically free. And it says, searching for data and you're okay. And then there's a tier 4, or the upper version. We'll call that significant redundancy. The term they use, 2n plus 1. So if you need 10, you get 21 widgets or units. In this significant redundancy space, right, there's really, not only is leakage going to be an issue, downtime, right, the ability to keep these products up. And then finally, so serviceability. So we kind of say leakage, serviceability, and downtime. So having a reliable design. Clearly, efficiency or energy efficiency is important, but all of these new heat rejection solutions, they're very, very efficient compared to air-cooled. Again, even if you design it poorly, it still has physics, or the density of the liquid's 1,000 times more dense. So even if you've done the worst job of designing the new engine, internal combustion engine, you still are far better than any horse that's ever run.
Okay. Yeah, very interesting. You said there that obviously it's a big challenges, that there seem like there is a lot of quite small differences between the two setups as well. So I'm thinking more from like a personnel level now. So when you kind of bring in the personnel to do this work, or you bring in the team, what should they be thinking about when they need to adapt?
So when we're making this adaptation, first of all, we think brown versus greenfield. So do I have space today and I just need to fit what makes sense? Secondly, I'd say, hey, I get to start from scratch. Let's do a little bit of both. So if I have to fit what makes sense today, I have a brownfield site. I'm managing, 10,000 square feet of racks, thousands of racks. And I know that I need 10% increased densities just because that's the SLA, or the service level agreement from my customers. You're going to look at really 2 solutions. One, can I actually just remove that load from the rack and blow it right into the white space and have it absorbed by other parts of the load? No different than when you're in your home and you run your oven and you cook a turkey. We love turkeys in the US. You open your oven and it just spills out the heat, but it gets absorbed into the natural loads of the home, and it's not an issue. It's very common if you have low numbers, 10, 15, 20% rack increase. So in the brownfield sites, think of more of an appliance. They use the word CDU, cooling distribution unit. Think of it as a water-to-water heat exchanger, something the size of a refrigerator. And as an appliance, it could sit in the white space with your racks, and then you can just reject either into the space or onto some units to the roof. If we're talking greenfield, meaning all new, there's opportunities really to get away from this appliance, or, hey, I have a fixed size, and you could almost go to a skidded solution, or an alternatively above the rack solution. Remember that the white space is very valuable. When I say white space, that is where the server racks are located. This is we commonly call the dance floor, or where the money's made. So one rack, about 7 feet tall, 2 feet wide, 3 feet deep, it's going to rent for about $2,500, $3,000 per month. So, divide that by 8, right? That's 8 square feet. You're talking the better part of $500 a square foot for rent. So you can imagine anytime you are using the white space that doesn't have a rack on it, you're losing money. So can you put it above? Can you put your cooling system above the rack? Or could you put it in the mechanical rooms and pipe it in? Because it's not air, you can actually transfer the heat in tubes or pipes, very similar to what chill water or DX systems do today.
Okay. Yeah, very interesting. And it sounds like that's a challenge, but also a big opportunity then, right? So what are maybe some of the things that people should be thinking about there when they're specifically looking into how to make use of that?
Mm-hmm. The industry hasn't really gravitated to a form factor. So if we imagine automotive cars, 1905, 1910, Henry Ford comes along, 1907, what size car should I build? Well, the roads really hadn't been finalized. How big was a road? Can I make the turning radius? What size should a truck be? So since the industry hasn't gravitated to a form factor, thinking in modules or building blocks makes a lot of sense. If you're building your racks at 50 kilowatts, 100 kilowatts, even more, and if you want to service 5 racks, 10 racks, 15, so you can imagine these units, if you do 50 kilowatts a rack and 10 racks, that's a 500 kilowatt unit. But if you want 100 kilowatts a rack and 10 racks, that's a 1,000 kilowatt unit, and the like. We've seen sizes from 400 kilowatts up to 1.6 megawatts or 1,600 kilowatts. So that's a 4x size difference. Significant. So instead of focusing on what makes sense in total, what am I going to go buy? Decide what makes sense for your business, your flow rates, and how you want to service. If your SLA agreements are typically in 5 or 10 rack sets, it makes a lot of sense. If your server agreements are a lot in 1 or 2 rack sets, then it might make sense to look at a different building block so then you can cool accordingly.
Okay. Yeah, very interesting. And is that, uh, I guess the challenge is there can't really be too much trial and error, as you say. People are obviously set with a task and they need to make sure it works. So will it be like a certain amount of installations that a team need to do to work that out, or what would you say around that?
So that's a great question. So when we talk about iterations, the way we think about it is, again, liquid cooling is so much more efficient than air cooling. You can design it poorly and it'll still be okay. The industry throws around a term PUE, that's a power usage efficiency. In general, if whatever the watts your servers pull, it's how much incremental your power system. So if your your servers pull 100 watts and your cooling system pulls 20 watts, the numerator is 100 plus 20 divided by 100. So it's a 1.2. So air cooling systems are 1.2, 1.3. They're pretty good now, 1.1 and maybe lower. These liquid cooling systems, 1.03, 1.05, so they're already 50% better than the best air cooling system out there. So if they're already 50% better, focus less around total efficiencies and more around applicability, serviceability, and having a high confidence solution. There's several businesses out there that do these liquid cooling type connections and solutions. They've been around for a decade, and they have a proven track record of success. So I'd say focus on minimizing risks as opposed to optimizing your efficiency, as the efficiency is already significantly better than it was before.
Yeah, interesting. One solution you mentioned at the start of this conversation was the hybrid model of like 20% air, 80% liquid cooling. Maybe just expand on that a little bit in terms of how that works. What are some of the kind of key advantages of that?
Mm-hmm. So when we talk about this 80-20, everyone loves 80-20 rules. They're so much easier to think about. We like rules or structures. It helps us to move forward. So it's been thrown out there, and we always say it's not right, but it's not wrong, right? Is it 75-25? That's close enough. The theme being, when you have your heat rejection of 100 units, 100 watts, 100 kilowatts, 100 tons, 80% of it is going to be going to the liquid systems, and 20% will be going to the air systems. You actually could still have significant number of air cooling units, just either the flow rate will be down or the capacities will be down and you'll have more of them because you'll still have to have redundancies. Again, we talk about that tier 4 data center. So they call 2n plus 1. So I'll either have, if I had to have 5 air conditioners, I could have 11. I possibly can have larger air conditioners with, say, multiple systems inside. So complete redundancy within the unit. So if I have a 100 kilowatt unit, it might be two 50 kilowatt building blocks. So if one goes down with the controls and fans, I can still run the other. So summary, you're still looking at these building blocks. You're still seeing how they connect. The total we see is roughly 4 out of 5 cooling units of cooling total thermal capacity. The liquid cooling solutions, or the CDU, common term, cooling distribution unit, will absorb about 4 out of 5. And that other 1/5 is, again, going to go to potentially human occupancy. You'll still need to maintain humidity in the space. Remember, in normal commercial, humans breathe, they're adding humidity to the air. They do a lot more, term is DOAS, dedicated outdoor air systems. In these data centers, we need to add humidity. So how best to add it? Well, either entrain it right there in the cooling solution, or you'll, obviously mist directly into the air and still need to move the air with some sort of an air conditioning system, airflow.
Yeah, interesting. And are there any, like, I guess, design challenges or challenges that we should think about specifically for the hybrid model?
So when we think of challenges, obviously, hopefully everyone thinks of an opportunity, because I know I'm an engineer and that's how
Yeah.
we get paid, right? If there was no challenges or nothing to do, like shit, they don't even need us. So I like it, right? We think of like attorneys or lawyers, right? You got to have problems and then you need them. So these challenges, almost we look at it as a gift. And the challenge is, hey, I'm running at higher temperatures. I'm running at higher capacities. So my temperature in my normal human occupancy or commercial space is maybe 70F, let's 15C or something, throw out a number. These data center chips now can run at 100F to 25, 30C. They're running much, much higher temperatures. So one side, oh, that's a challenge. The other side say, what's the gift? The gift is Mother Nature. So typically these data centers, let's say they're running, 100 degrees Fahrenheit, 30C or whatever that is, 25C. As you're running those temperatures, what's the percentage of time that Mother Nature is roughly, 20 degrees Celsius or less? So if you want to make 25C cooling within your data center, then the data center space, the Mother Nature is often below 20C or below. So you could use what we call chillers or DX systems that go into free cooling or economization modes where they turn off the compressors. But the other gift is, hey, what about looking at solutions that don't even have compressors? For example, dry coolers. All we need to do is recycle that fluid because it's Mother Nature's 20 degrees centigrade most of the time outside or below. And my data center is very, very happy with 25C. So it allows us to balance those loads and then further reduce the power draw on the systems.
Interesting. You said Mother Nature then. So how aware do we need to be about the physical location that we're working with then?
So there's a couple of things that matter with a data center, right? You want to be close to the fiber. So we know the fiber patterns from the eastern seaboard of the US up to Ireland and Amsterdam. The western seaboard of the US goes to Asia. I love to speak US centric. That's Americans, right? You can see the cable patterns, but you can imagine anywhere where it's cold and dry is the best. And cold and wet could work. And when I say cold and dry, that means you can add humidity to the space and significantly change the heat loads. So anywhere where it's always cold is always best. And if you go to the warmer climates, you'd say you want to be warm and dry versus warm and wet. So say a Phoenix would be more appropriate, say, than versus a Florida, so for the US. So we can imagine that that's the goal. The term they use is a psychrometric chart. Mr. Carrier figured this out like 100 years ago. Smart dude. All the, basically psychrometric chart is humidity versus humidity versus temperature and the relative differences. You want to be either cold or warm and dry. Those are kind of your ideal locations to start.
Yeah. Sure. No, that's interesting. I mean, I know there's a lot of news, especially even today, there was some news around Saudi Arabia that are putting a lot of this kind of stuff in place and will look at cooling solutions. So I guess it's interesting just to think about when you say Mother Nature, if they're actually putting something in a location like Saudi Arabia, how that will work in comparison to places that are less hot, I guess.
Yeah. You could take the Saudi Arabia, say, versus Frankfurt or something like that. So Frankfurt's going to have a little higher temperatures. The humidity is going to be higher. So your workload per unit is going to be significantly more. Even though the heat load might be higher, there are solutions out there, typically called a direct evaporative media. So very, very simple design. The downside is it uses a lot of water. But if you have a relatively infinite supply, or you can have access to, that is less of a concern.
Yeah, interesting. Okay, I think again you mentioned this earlier around the kind of heat rejection challenges and managing the limited roof space. Again, that is often cited as like a very big challenge, especially with roofs already being very crowded, as you say, and kind of condensed. So, how are data centers overcoming this?
So it's actually getting, I would say, even magnifying the problem. So because we want to get close to the fiber, or they want to be close to the fiber, the data centers are typically going multi-story now. So if I had a one-story building and I filled the roof, now I have increased density, which already hurts it adds stress to the system. And now I want multi-story. So if I go multi-story, 2 or 3 stories, I really need like 4 equivalent roof spaces to handle all of my loads. So really one is to look at the higher temperatures. That's the gift, right? In every problem and there's an opportunity, right? So take advantage of the higher temperature or the differences in the temperature. And secondly is look at alternative. We talked about the liquid cooling. And then thirdly, you can imagine if you were to rotate. So a lot of these cooling units sit with coils horizontally. If you go coils vertically, you could potentially stack, different form factors to get more. The top downside is crossflow. So your condensers or your outdoor unit typically controls a lot of the capacity of your unit. And if you have a crossflow, like a nice heavy, a wind gust, for example, or the lack of, you can imagine all of your units next to each other. If they're horizontal, they could have some crosstalk in terms of the temperatures or the airflows and could cause a little bit more of a controls challenge. But they have a lot of smart people out there that get to balance those for us.
Yeah, no, interesting. Is there any like alternatives then around the heat rejection strategies that are being thought about?
Mm-hmm. Yeah, top one really would be around dry coolers or again, systems without compressors. And then you can also imagine these dry coolers with additional, I call misting or the ability to add humidity to that condenser. So if you locally increase the density of the air, it can then absorb more. Said another way, if I put on your hand a 100-degree Fahrenheit hair dryer, that feels comfortable. But if I pour 100-degree water on your 100-degree Fahrenheit water on your hand, you go, oh, that's hot, because it's 1,000 times more dense. So if I increase the local density right at that unit, hence the misting, you can cheat Mother Nature into absorbing more heat.
Yeah, very interesting. Okay, cool. So I think on the kind of the rack density piece then, as you mentioned earlier, the rack densities are continuing to increase. They're getting bigger. They're getting more equipment put into the racks. How do you manage localized heat within these racks then, when it comes to specifically within the white space?
So there's really a couple. So that's a great question. So within the rack, let's call it a 42U. So you have 42 servers in a rack today. A U is a 1.75 inches. So if you have a 6U server, it's a better part of 11 inches tall, and it's a building block that sits within the server racks. There is a service level agreement or SLAs always from the end customer, whether it's a hyperscaler, a colo, enterprise. We have an agreement. My servers are going to be fed 70-degree or 75-degree air, plus or minus 2 degrees. So there's really kind of two pieces. Number one, so if we can build a more robust system, in general, they can raise the server loads. Right now, we call ride through, or if you imagine your job is to ensure those servers are cooled, you might run your data center a couple degrees cooler than it actually needs to be. In the event that something goes down, you actually have a minute or two for while the temperature is rising that you're still within the service level agreement. But if then people are providing more high confidence solutions, improved robustness, improved reliability, then you might consider driving down or driving up that temperature. So if you need 75-degree air, run it at 74 instead of 70. Secondly is around increasing the flow rates. So within the racks, there's numbers 4, 5, 600 CFM, feet per minute across a rack of velocity. Do you increase that velocity a little bit to ensure you're getting a good flow? Conversely, if there's a lot of cabling, you might want to actually decrease that flow rate to ensure you're getting coverage through that rack. So you do want to look at someone that can help you, whether it's CFD, computational fluid dynamics, or a tool like a digital twin that would help you balance how that heat load could starve any particular racks within your solution.
Interesting. You said again earlier on in the conversation that a lot of the new AI technology specifically is producing a lot more thermal output, right? So is that what you mentioned just there? Is that specifically the advances in the AI chips and the hardware, or what are, again, some of the kind of concerns around that?
Yeah, so it's the chips, right? So not only is it the chip itself, but how many chips per server now can you seat? So again, if a chip is going from 600 watts to 800 watts and you have 4 chips, that's one thing. But if those chips additionally are getting smaller and hotter, now you go from 400 to 600 or 600 to 800 watts, and you go from 4 to 10 chips or 4 to 8 chips. So your total load is obviously the number of chips times the difference in the densities per chip. So we see those only increasing. We used to think 100 kilowatts a rack was a lot. Some have said now going to 200 kilowatts a rack. The point is, it's human nature. We're always going to grow. We want to be better. And heat is the work being done. So you can only imagine that as those servers get smarter, even if they're more efficient, you'll see that temperature continue to rise, or those heat loads continue to increase.
Yeah, very interesting. And you've kind of touched on there, looking ahead into the future. So I think with that in mind, again, it'd be really interesting to hear your thoughts around how you see, I guess, the next 5, 10, 15 years. How do you think that the current setup that we have today needs to be evolved, let's say over the next 5 years, to meet the demands that it needs to?
Most of the cooling OEMs out there are full for the next year or two of capacity. So they booked up, hey, I want this widget, and it's, the facilities are full, right? It's the opposite of COVID, right? We were looking to fill facilities, and now they're full with work. So it's more of an operational OpEx play. So today they're building out a lot of these large scale 100 megawatt, gigawatt campuses and the like. The next play is going to be the edge play, because you'll still have latency issues getting your data out to the customers. So do we foresee a large volume, but smaller scale of units? Think of the bottom of a cell phone tower. Maybe think of every stoplight that you go as you're driving in a city. You're going to, at least for sure in the rural areas, you're going to need some sort of local data processing. Does this include some sort of a modular type unit that is able to process information real time and get it back to you, say, for a smart driving car? These solutions aren't going to be gigawatts and megawatts. They're going to probably be measured in less than a megawatt or 100 kilowatts. And these could have the form factor of 30, 40 feet or whatever that is, 10, 13 meters, or they could even be smaller. So you can imagine after years 3, 4, 5, there's going to be this modular play. I need to get the data out to the people in a smaller physical size, enabling it closer to the customer. So we kind of see. And then thirdly, you can imagine as the data continues to get smarter and we tier these data centers, tier 1, meaning I'm processing information, it's okay, it goes down. I tolerate latency. Maybe those continue to go into further colder temperatures in the world because Mother Nature's our friend. And what else do we do with that heat load? So we do like regenerative heat or heat recovery, regenerative turbines, regenerative compressors. So you'll have a heat load. and you either could heat something local, like a swimming pool in an area, or a natatorium, or you could actually potentially even heat local farming locations. So you'll have soil, and you might have some sort of a heating lattice or an array, such that that data center that's in a northern Nordic country could potentially be more profitable or more usable for their land and farming spaces year round.
Yeah, very, very interesting. Um, I guess what I'm thinking, the last kind of couple of questions on my mind is when you're speaking to like peers of yours, right, and speaking to CTOs who are responsible for running this, what are some of the things that we should be aware of to really future-proof the kind of infrastructure and what they're doing today that maybe, they haven't thought about?
Good one. I would say it's almost they think about it, but not most broadly. There's kind of two more modeling. So digital twin is a common term, but we've had modeling. Engineers, we do FEA, finite element analysis, CFD, computational fluid dynamics. The idea is you have boundary conditions and you optimize within your plan. You look at different thicknesses, flow rates, and the like. They have these digital twins, making them more accessible. So there's a lot of major players in the world. Emphasis is an example. HCL, these companies that have broad-based brains that can help bring this digital twin to some of these smaller businesses, so they can model their design up front and they can interrogate or stress test it. What happens if this goes down? What happens if I lose this control? So not only do they do Upwork modeling, they do Upwork control algorithms. So it's not only around measurement, but it's around realization. Example, if you have a chill water pump and you're constantly changing flow rates, your valve is always hunting. But if you can imagine that valve works in harmony with the pumps, works in harmony with the cooling unit and the servers, then you can imagine, hey, I see my server load coming. There will be a call for cooling. Let's ensure my valve doesn't continue to hunt and burn out energy and continually to wear itself out. So having the components work in harmony as a team, much, much more efficient in terms of total designs and robustness.
Yeah, thank you. That's great. Okay, cool. So just to kind of wrap up then, the final thing I'd love to ask you, Lorenz, based on, everything we've discussed over the last 30 minutes, if you were to give, your top three quick fire advice to someone watching this, what would that be?
I would say think about the efficiencies of these systems and don't worry about going after the small. Focus on the most important. Like if you're doing liquid cooling systems, high density, focus on leak proof, focus on the form factor that makes sense, and let the efficiencies go for the ride. If you try to over design your system, you're going to end up slowing down execution and potentially risking some stumbles. So I'd say focus on the high risk points when you know that things are going to benefit you on the upside on the efficiency. Number two, think about where we're going next in terms of sizes and footprints. Today, we're building out large spaces, 100 megawatt, gigawatt. We know that behind that will be a next generation of sizes, smaller, closer to the customer, more deployments. And then thirdly, I would say we didn't talk about it, but imagine there's barriers to entry. There's regulatory, there's bring your own power, right? Do I even have the ability to receive power? And or the ability to get land. So as you imagine you're in a data center space, how do I minimize those barriers to entry? Conversely, if you're developing new products, how do I maximize those barriers to entry and make it more challenging for others to come in and play in my sandbox? Those kind of would be the three.
Yeah, very interesting. On point three, could you give any kind of expand on that a little bit in terms of what you're seeing or what you're thinking or?
Mm-hmm. So if you can imagine, let's just use an example, regulatory. So if regulatory says, hey, there's a risk around alternative refrigerants, and that risk is going to be in the white space. So in the white space, meaning where the data centers are, there's companies today that sell solutions that have white space impact. However, they're those are some of them, the bigger ones are very, very smart about innovation. Do I A, move to a chill water solution, or B, move to alternative refrigerants? Or C, have some sort of a system that is both, kind of a DX outside and moves the water on the inside. So they're working on solutions. Some have implemented faster and more than others. They're global companies, you've seen them. But the idea is they're using the regulatory impact not as a thorn, but instead as a rose or as the rose petals, to using it as a benefit to further grow and expand within the business.
Perfect. No, that's very interesting. And yeah, really appreciate getting your thoughts on this topic, Lorenz. I think yeah, it will be great for people. Hopefully they can watch or listen to this and really take some things away. If someone is watching this and they've got some questions, maybe they wanted to ask you, what's the best way that they could reach out or get in touch with you?
Sure. So I'm Lorenz Hofmann. I'm on LinkedIn, and my email is the same. It's Lorenz Hofmann at Yahoo. So Hoffman has one F and two N's. You'll see me out there on LinkedIn, and would love to interact as we go forward.
Yeah, perfect. I'll attach your LinkedIn link somewhere around the video. So yeah, I guess if people have got questions, they want to pick your brain or have a conversation around some of the things you've mentioned, Lorenz, they'll be able to find you. But look, I just want to say a massive thanks as well. I think this has yeah, been very useful. Hopefully people can watch this and really get a lot of insight into it. So really appreciate your time.
Thank you very much, Charlie. Appreciate it. Have a good day.